Hello, everyone. You are listening to Uncomfortable Truths with Euclid Phoenix, where I talk about politics, religion, and other BS I find interesting. Today, for other BS, I'm going to talk about quantum physics and the quantum internet. Quantum physics is explained. The strange science that empowers the modern world. Quantum physics is often portrayed as one of the most mysterious and mind-bending areas of science. That is the branch of physics that studies the behavior of matter and energy at the smallest scales imaginable: atoms, electrons, photons, and other subatomic particles. If you've ever heard statements such as particles can exist in two places at once, observation changes reality, two particles can communicate instantly across vast distances, then you've encountered some of the strange ideas associated with quantum physics. Because these concepts sound so bizarre, many people assume quantum physics is little more than an abstract theory with little connection to everyday life. The truth is the exact opposite. Without quantum physics, much of modern civilization would not exist. The smartphones in your pockets, the computers on our desks, GPS navigation, lasers, medical imaging devices, and much of the internet all rely on technologies built upon quantum physics principles. In this podcast, we'll explore what quantum physics is, why it appears so strange, and how it quietly shapes the modern world around us every day. What is quantum physics? Quantum physics is the study of nature at extremely small scales. Classical physics, the physics developed by figures such as Isaac Newton, works extremely well when describing baseballs, planets, cars, buildings. However, when scientists began studying atoms and subatomic particles in the early 20th century, they discovered that the universe behaves very differently at tiny scales. The old rules no longer worked. Instead, particles appeared to behave in a way that defied common sense. This led to the development of quantum mechanics, one of the most successful scientific theories ever created. The quantum revolution. Several scientists helped create quantum theory, including Max Planck, Albert Einstein, Niels Bohr, Erwin Schrödinger, Werner Heisenberg. Their discoveries revealed that energy and matter are not always continuous. Instead, many physical properties occur in discrete packets called quanta. This insight completely transformed physics. Wave-particle duality. One of the first strange discoveries of quantum physics was that particles sometimes behave like waves. For example, an electron can act like a particle, but under certain conditions it also behaves like a wave. Light behaves similarly. Sometimes light acts on a wave. Sometimes it behaves like individual particles called photons. This phenomenon is known as wave-particle duality. It challenges our everyday intuition because objects in our normal experience are usually either particles or waves, not both. The double-slit experience. Perhaps the most famous experiment in quantum physics is the double-slit experiment. Scientists fired particles such as electrons toward a barrier containing two small openings. Surprisingly, the particles produced an interference pattern similar in waves. Even stranger, when scientists attempted to determine which slit each particle passed through, The interference pattern disappeared. The results seem to suggest that observation somehow affects outcomes. This experiment remains one of the most fascinating and debated findings in science. Quantum superposition. Another strange concept is superposition. According to quantum theory, a particle can exist in multiple possible states simultaneously until a measurement occurs. A common illustration is the thought experiment known as Schrodinger's cat. In this famous scenario, a cat is described as being both alive and dead until the box is opened and observed. The example is not meant to be taken literally, but demonstrates how quantum systems can exist in multiple possibilities at once. Quantum entanglement. Perhaps the most mind-bending phenomenon is quantum entanglement. When particles become entangled, their properties remain connected regardless of distance. Changing the state of one particle immediately influences the description of the other. Even Albert Einstein found this troubling and famously referred to it as spooky action at a distance. Today, entanglement has been confirmed repeatedly through experiments and is becoming a foundation for future technologies. How quantum physics is used today. The most surprising thing about quantum physics is how practical it has become. Many modern technologies exist because scientists learned how to harness quantum effects. Computers and semiconductors. Every computer, smartphone, and tablet relies on semiconductors. Semiconductors function because of quantum behavior within materials. Without quantum physics, laptops would not exist, smartphones would not exist, modern computing would not exist. The digital revolution is fundamentally built upon quantum principles. Lasers. Lasers are used in barcode scanners, fiber optic communication, medicine, manufacturing, and entertainment. Laser technology relies directly on quantum transitions within atoms. Without quantum mechanics, lasers would remain impossible. Medical imaging. Modern medicine uses quantum principles and technologies such as MRI machines, PET scans, advanced diagnostic equipment. These technologies allow physicians to observe internal structures without invasive surgery. Millions of lives have benefited from quantum-based medical tools. GPS navigation. Many people are surprised to learn that quantum physics helps your GPS function correctly. GPS satellites rely on extremely precise atomic clocks. Atomic clocks operate according to quantum principles. Without these clocks, GPS systems would quickly become inaccurate. Every time you use navigation on your phone, you're benefiting from quantum physics. Solar panels. Solar panels convert sunlight into electricity through the photoelectric effect. This phenomenon was examined by Albert Einstein using quantum theory. As renewable energy expands worldwide, quantum physics continues to play an increasingly important role. The future, quantum computing. One of the most exciting developments today is quantum computing. Unlike ordinary computers that use bits represented as 0 and 1, quantum computers use quantum bits or qubits. Because qubits can exist in superpositions, they may eventually solve certain problems dramatically faster than conventional computers. Potential applications include drug discovery, cryptography, artificial intelligence, materials science, climate modeling. Although still in its early stages, quantum computing could become one of the most important technologies of the 21st century. Does quantum physics mean reality is weird? One reason quantum physics attracts so much public interest is that it raises profound philosophical questions. Scientists continue debating how quantum mechanics should be interpreted. Some interpretations include the Copenhagen interpretation, the many worlds interpretation, pilot wave theory, objective collapse theories. Oh, come on. Sorry about that. Times this. Okay. Each attempt to explain the quantum mechanics is actually telling us about reality. Remarkably, these interpretations often make the same predictions while offering very different explanations. This means physicists still disagree about what quantum theory ultimately means. Common misconceptions. Quantum physics is often misunderstood in popular culture. It does not prove telepathy, magic, manifestation, supernatural powers. While quantum mechanics is undeniably strange, its predictions are based on careful experiments and mathematical models. Many popular claims misuse scientific terminology without supporting evidence. The general science is already fascinating enough without exaggeration. Conclusion. Quantum physics is one of humanity's greatest scientific achievements. It revealed that reality behaves in ways far stranger than our everyday experience suggests. Particles can behave like waves. Objects can exist in superpositions. Entangled particles can remain connected across great distances. Yet quantum physics is not merely an abstract theory. It powers computers, smartphones, lasers, medical technology, GPS systems, solar panels, and so on. In many ways, modern civilization is built upon discoveries that once seemed impossible. As scientists continue exploring quantum computing and other emerging technologies, quantum physics will likely become even more important in shaping the future. The deeper we look into the quantum world, the more we discover that reality is far stranger and far more fascinating than anyone imagined a century ago. Now I'll talk about the quantum internet, how entanglement could redefine communication. Spooky action at a distance, Einstein once called it, but quantum entanglement might one day allow us to build a new kind of internet, one whose rules challenge our deepest intuitions about information, causality, and connection. What is the quantum internet? In simple terms, the quantum internet is a communication network that doesn't just send classical bits, zeros and ones, over copper or fiber, but sends and manipulates qubits, quantum bits. These qubits can exist in superposition, both 0 and 1, and can become entangled with other qubits so their states correlate strongly even when separated by large distances. It's not just a better internet, it's a functionally different type of network. It would support new protocols such as quantum key distribution for near unhackable encryption, quantum teleportation of qubits, i.e. transferring the state from one location to another, entanglement swapping, and quantum repeaters to reach distributed quantum computing and sensing, where devices share quantum states. Super-dense coding, where more classical information is sent per qubit via pre-shared entanglement. The goal is a network where quantum models, quantum computers, sensors, storage units can exchange quantum information securely, reliably, and over large distances. Entanglement, the heart of the quantum internet. Entanglement is the mystical glue that holds much of this together. Here's how. Correlated states. Two or more particles become entangled so that measurement of one immediately yields information about the other, even far apart. Resource for teleportation. If Alice and Bob each hold halves of an entangled pair, Alice can send a qubit state to Bob by using that entanglement plus 2 classical bits. That's quantum teleportation. Enabling QKD. Many quantum secure encryption schemes rely on entanglement to detect eavesdroppers. Any attempt to intercept or measure the entangled particles disturbs them and can be detected. Super dense coding. If Alice and Bob share an entangled pair, Alice can encode 2 classical bits of information by applying one of 4 operations to her qubit, then send just the one qubit to Bob, who decodes it using the pre-shared entanglement. However, and this is critically important, entanglement by itself cannot be used to send classical information faster than light. That's forbidden by fundamental quantum rules. This constraint is formalized in the no communication theorem, which ensures that quantum mechanics does not violate causality. So in practical quantum internet designs, classical communication is still needed alongside quantum channels. How would a quantum internet work in broad terms? Here's a step-by-step sketch of how nodes might communicate in a quantum network. Entanglement distribution. A source device produces entangled qubit pairs, photons, electrons, etc. One half goes to node A, the other to node B, or through intermediate nodes. Quantum memory and storage. Nodes must be able to store quantum states coherently, and so further operations are ready. Quantum repeaters, entanglement swapping. Because photons traveling through fiber lose coherence and are absorbed, direct long-distance entanglement breaks down. Quantum repeaters or nodes perform entanglement swapping. 2 shorter entanglement links can be combined, swapped to extend entanglement over longer distances. Teleportation and classical channel. To send a qubit state from A to B, you use quantum teleportation. A enter X its qubit with its shared of entanglement performs a measurement, sends the classical result 2 bits to B, and B uses the classical information to reconstruct the state. This ensures the qubit's original version is destroyed and at A no cloning and appears at B. error correction and purification. Quantum states are fragile. Errors, noise, and decoherence occurs. Purification protocols or quantum error correction must clean up noisy entanglement states before use. But there is no universal purification method that works optimally in all cases. Advanced architectures consider entanglement assisted error correction, sharing extra entanglement ahead of time. Network architecture and routing. Because entanglement links can succeed or fail probabilistically, the network has to dynamically route and manage which nodes are entanglement, when to refresh links, etc. Some recent proposals use hierarchical architectures to reduce overhead and optimize routing. Integration and classical networks. In practice, quantum signals will often travel alongside classical data or through existing fiber infrastructure. New research shows it's possible to bundle quantum and classical signals in the same optical fiber using hybrid chips. What challenges must be overcome? Whilst the idea of electrifying the real world engineering is brutally difficult, some of the biggest challenges include decoherence and loss. Quantum states are extremely delicate. Photons can be absorbed or scattered in fiber, and quantum states can degrade over time. Limited range. Direct entanglement over fiber only works reliably over tens to a few hundred kilometers. Without repeaters or satellites, scaling it impossible. Quantum memory and interfaces. Efficient interfaces between photons used for transmission and matter-based quantum memories, atoms, ions, NV centers, solid-state systems are still under intense development. Error correction, purification limits. As mentioned, there is no universal optimal purification protocol. One size does not fit all systems. Network stability, because entangled leaks consumed, for example, collapse upon measurement, and links can fail. Networks must continually rebuild and adapt. Some recent proposals add bridges to stabilize networks. Scaling and routing. As the number of nodes increases, the combinatorial complexity of entanglement distribution, pathfinding, and resource allocation becomes enormous. Cost, hardware constraints, and cryogenics. Many quantum devices still require extreme cooling, specialized optics, and highly isolated environments, making them rugged, mass producible, and cheap is a steep climb. Integration with classical infrastructure. Ensuring quantum systems play nicely with existing fiber networks, routers, and control systems is non-trivial. In short, we have many promising experimental demos, but turning them into robust global quantum internet is one of the major moonshots in modern science. Why it matters, the potential upsides. Why would a functioning quantum internet change? Ultra high security and cryptography. cryptography, because any eavesdropping attempts disturbs quantum states. It's possible to design communication in which any interception is detectable. This leads to encryption methods like KDD, whose security is grounded in physics, not mathematical complexity. Distributed quantum computing and sensing. Multiple quantum computers, sensors, or nodes could share quantum states and work collaboratively. You could perform tasks that no single device could do alone. Improved precision measurements. Entanglement enhancement sensing could allow for gravity measurement, navigation, timing, or telescopes far beyond classical limits when nodes are entangled across distances. Future-proofing against quantum attacks. Quantum computers eventually threaten many classical encryption schemes. A quantum internet offers built-in resistance to such attacks by design. New information theoretic paradigms. The existence of entanglement changes how we think about information, correlations, and causality. It opens doors to new communication protocols that have no classical counterpart. Misconceptions and clarifications. Entanglement does not equal instant messaging. You can't use entanglement to send a message faster than light. That's precisely what the no communication theorem rules out. Teleportation isn't Star Trek teleporting of matter, it's teleporting the quantum state. The original is destroyed. The no mass moves faster than light. Quantum does not equal always better. Classical networks will remain important and in many cases preferable for bulk, robust, low-cost communications. The quantum internet is a complement, not a total replacement. Pre-shared entanglement is a resource. Many quantum protocols rely on entanglement that has to be created and maintained ahead of time. It isn't free. Experimental proofs versus real-world scaling. Many demos are in labs over short distances, cold conditions, or with limited nodes. Scaling to practical networks is orders of magnitude harder. Recent breakthroughs and future direction. To show this is not just speculative, here are some recent advances and active research frontiers. Researchers have demonstrated device-independent quantum key distribution schemes that no longer assume you must trust that hardware is flawless. A Q-chip has been built that allows quantum and classical signals to travel together over existing fiber networks and use standard internet protocol routing. That means quantum signals can ride along on today's infrastructure. New methods have shown ghostly quantum communication where information is effectively transferred without occupying the intervening channel by using entanglement between nodes. Proposals for hierarchical quantum network architectures aim to reduce maintenance and improve routing efficiency compared to flat architectures. Satellite-based quantum repeaters with quantum memory have been studied for global scale enlargement distribution, which could leap over the distance limits of fiber. The trajectory is promising. What once was considered science fiction is becoming feasible in a lab setting, and increasingly real-world tests are being done. That's it for today when it comes to other BS. Please visit my site below, sign up for my newsletter, and support me on Patreon. Thank you for listening, and have an awesome day.